Today we're going to talk about section 7.1, which deals with oblique triangles and the law of sines. Up until now, everything we've done in trig has either had to do with circles or right triangles. Okay? SOHCAHTOA, Pythagorean theorem, arc length, area of a sector, all of those things are only for right triangles or circles. But a lot of things in the real world don't deal with right triangles. So chapter 7 is all about talking about things that are not right triangles. Anything that's not a right triangle, any triangle that does not have a right angle is called an oblique triangle. So a triangle that is not a right triangle is called an oblique triangle. And the nice thing about this chapter is that this chapter works for any triangle, oblique or right. So I don't really understand why we don't do more of this in geometry. We spend so much time on SOHCAHTOA, but if this also works for right triangles, then I think we should spend a little more time on this. So this is probably one of my favorite sections. So here's what you kind of need to know to get you started. The measures of the three sides and the three angles of a triangle can be found as long as you know at least one side and any two other measures. Okay? You have to know at least one side. Does anyone know why? Well, what if I said it's an equilateral triangle, right? So every angle is what?
60 degrees.
And every side is the same. So each of those is 60. And if I know those three, can I figure out this side?
No.
No. That could be a really big triangle or a really small one. So unfortunately, a triangle is solvable almost all the time, but you have to know at least one side and two other things about it. It could be a side and an angle, it could be two angles, or it could be the other two sides, but you have to know something. Okay, so depending on what you know in this chapter, you know, what the given situation is, whether you know two sides and an angle, whether you know two angles and a side, that sort of thing. Depending on what you know, there are different cases. And today we're only going to talk about case 1. So I recommend that you only deal with one case at a time, even though your book introduces all 4 cases. Let's see. Case 1 is section 7.1. Case 2 is 7.2. And we will do cases 3 and 4. They are section 7.3. So today we're only going to talk about case 1, and it depends on what you're given. In case 1, we know one side and two angles. It could be any one side and any two of the angles is what you're given. Does that make sense? And that's all you need to know for today. We'll pause for a second and see if you want to take some notes. Okay, so one more time. Case 1 is all we're doing today. You will be given one side and any two angles. From geometry, you may remember that as angle, angle, side, or angle, side, angle. All right? We're going to go ahead and we've talked about this, point out that if we know 3 angles of a triangle, we can't find unique side lengths since angle, angle, angle only assures us similarity, not congruence. Angle, angle, angle was not one of those in geometry either, okay? Here's the law of sines. The law of sines states that for any triangle ABC with side lengths little a, little b, and little c, and angles capital ABC, it is always true that any of the sides divided by the sine of the angle opposite that side will equal any other side divided by the sine of the angle opposite of that. Of that side. Okay, so you always have 3 choices. You can do A over sine A equals B over sine B, or you can do A over sine A equals C over sine C, or you can do B over sine B equals C over sine C. So it doesn't matter which 2 you use, they have to be equal, which means that as long as you know one side and 2 angles, you can solve any triangle with a basic proportion. So these are just proportionalities. It should always be true that any side divided by the sine of its opposite angle will equal any other side of the triangle divided by the sine of its opposite angle. law of sines. So for our first example, here's the information we are given. We have a triangle. We know that angle A is 32.0 degrees, angle B is 81.8 degrees, and side little a is 42.9 centimeters. So notice we are given one side and two angles. So if we want to completely solve this and find the three missing measures, that means I am looking for capital C, I am looking for little b, and I am looking for little c. So those are the three things that I need to find in order to be finished with this problem. Does that make sense? Mm-hmm. Okay. One of those things is really, really easy to find. What is it? Capital C. Yeah, we know that in a triangle, the angles have to add to exactly 180 degrees. So if you know two angles, you can always find the third by taking 180 and subtracting the others from it. So let's do that first. Let's find capital C. So what do we get for capital C?
66.2 degrees.
66.2 degrees. Okay. Now usually what I've noticed about your book, and it just kind of depends on the instructor and the textbook, with angles in a triangle, they typically don't worry about sig figs. They just make sure that it adds exactly to 180. Does that make sense? Mm-hmm. So most of the time, because 180 is considered an exact number for triangles, they don't worry about sig figs with those. They just make it add exactly to it. Okay? All right, so we have 66.2 degrees is angle C. And now we need to find either little b or little c. And it doesn't really matter which. Which one would you like to find first?
Little b.
Little b. Okay, let's try to find little b. In this situation, when I know one side and two angles, and technically now I know all three, but I started with one side and two angles, I need to use law of sines to solve for the other sides. So we will take little b, and we will stack it over the sine of big B, and that has to equal one of the other side lengths divided by the sine of the angle opposite it. And when you can, you need to use the given information as much as possible. So in this case, I know this, and these are a pair of opposites, and that's what you're looking for in law of sines. You have to know a pair of opposites before you can even get started with it. Okay? So in this case, we know that b over sine of 81.8 must equal a over sine of a, which is 42.9 centimeters divided by the sine of 32 degrees. Okay? So all we have here is a proportion. You solve it like any other proportion. Just very quickly, you cross multiply and divide it out and get what you need by itself. So if we cross multiply, we have b sine of 32 must equal 42.9 times the sine of 81.8. And then if we finish that, we just divide both sides by sine of 32. So let's put that in our calculator and see what that comes out to. Be sure that you are in degree mode. It does matter. Be very careful. Triangles are always done in degrees. So when I calculate that, I get 80.12805567. And what are my units? Centimeters. The lengths are given in centimeters. And then I need to round it to the appropriate significant digit. And so for this problem, it looks like we have three significant digits. So that would be 80.1 centimeters?
Yes, ma'am.
All right. So we are 2/3 of the way done. 80.1 centimeters. Not for the angles, is what I said. Okay. For the side lengths, for lengths, you're always going to, unless you know something is exactly a certain amount long, like you have to always use sig figs. But for the angles, we know they have to add exactly to 180. We have no idea about the sides, what they're going to make. So we obey the laws of significant digits there. Okay, so that's 80.1. All I'm missing now is little c. Do you know where most people make their mistake right here?
They use the rounded answer to do Pythagorean. Yeah.
Well,
They use
the Pythagorean. Why can we not? We can't use the Pythagorean theorem. It's not a right triangle. You can only use the Pythagorean theorem
For real,
if you absolutely know it's a right triangle. Same thing with SOHCAHTOA. If you don't know what kind of triangle it is, or if it isn't a right triangle, you can't use that. In fact, the only way we can solve a non-right triangle, the only thing we know right now is law of sines. So we're going to need to start over and do the law of sines again for angle C. For side C. So we're going to say C over sine of C. So see, in this case, we are going to have to use one of our rounded answers, 66.2, but it should be okay since it goes exactly to 180. And we're going to set that equal to either B over sine B or A over sine A. And once again, I'm going to caution you, use the ones that were given. Because if you use the B over sine B, it's sort of like you were pointing out, we can't use that rounded answer. So it's much easier to use the givens than the unrounded answers. So we have 42.9 divided by sine of 32 right here. So C over sine C equals A over sine A. And I'm going to let you guys do the calculations right there. And once you multiply and divide, tell me what you get.
74.07.
74 point 226. Do you guys know why I always write every one of these down? Do you know why? Just in case I have to use that side later, you always want an unrounded answer up there. So if I were going to use little b in this problem, I would need to get the unrounded, not the rounded. So if you're actually going to use it, then you need to go back and take the unrounded. All right, what does that round to?
74.1.
74.1 centimeters. Okay. So that's how we solved that. Now, how do you think you check this problem?
That's a good question.
You use the
You
proportions.
plug it back in
To what?
to C over sine of
Yeah, use the law of sines and pick any two sides. And take that side and divide it by the sine of its opposite angle. And it needs to equal. So pick, like, for example, take the givens. Take 42.9 degrees and divide it by sine of 32 and see what you get. 42.9 divided by sine of 32. Got it? Okay, now take, let's just check B. Now it's going to work out better if you take the unrounded. So take 80.12805567 and divide it by the sine of B, which is 81.8. Are those ratios the same?
Yes.
Yes. Are they the same all the way through? Okay. If you use the rounded answer, they will only be the same rounded to the significant digit. But if you use the unrounded answers, they will be the same to about 8 or 9 decimal places at least. Does that make sense? So remember that if you use the rounded, you have to round the ratios as well, and they should round to just about the same thing. I always prefer to check with the unrounded so that I can be certain. Okay, let's break there, and then we'll do some other examples.